Today I'm going to present about what I am responsible for in this Supersonic internal project. I will take all the dimensions calculated by my teammates and then draw a 2D model from it. Like in this one, this is our Supersonic wind tunnel model drawn in Fusion 360. Start off with drawing the inlet and the nozzle. The nozzle contour is produced by MATLAB from George the Engineer with the modified code from LAM that it is given me the .csv file, the coordinate of .csv file, so that I can just import that coordinate right into Fusion 360, and then it creates this curve for me, which is perfect contour to prevent any undesired shock wave. And with the tail section here, the tail section here is with a height of 18 centimeter with a wedge with a at a specification with the angle of 25 degree and the height of 6 centimeter. And also here the diffuser part, which is 15 centimeter high, which is more than the minimum value of 13.78 centimeter, because the flow did not start at the first time we tried this, so I have to increase the height a little bit to make the flow start and reach the wedge here. The flow may start, but it's moving very slowly. It might take in answers up to 200,000 iterations, and that takes up too much computational time and power. So by doing this, we'll reduce the computational times, because in real practice, some supersonic wind tunnels have the adjustable diffuser throat to make the flow move faster as well, and all the way to the end. The overall length of this supersonic wind tunnel is around 2.8 meters. And then after we've done this, before you end up with this, you will end up with only this, which is just a sketch, and this is not usable in ANSYS because ANSYS won't recognize what sketch is, even though you export it as IGS or step file. So before you go, you have to make it to be a surface by using this function called surface, and then you choose patch here, you click patch on here, you end up with this one. It turns into a surface for you. Now you can export it. Choose IGS file, and then you click export, and then you will end up with the IGS file on your desktop or wherever you export it to. Or the IGS file from Fusion 360 already. Now you're in ANSYS here. You set up the analysis by dragging geometry box down here, and then you have to select the IGS file you have export by clicking mouse here. You select the file, and then after that you open Design Modeler in here. Click Open Design Modeler. Okay. Now you have the you open the Design Modeler here, and then when you first import it, this thing will be in lightning symbol, so you just have to click Generate, and then it gives you this exact same dimension as you exported from Fusion 360, and you're done with this already. Now you can close it. Wait for it a little bit. And next up, you can open mesh by dragging the mesh box here and then connect it to geometry, and then you open mesh to edit it. And now you are here in the mesh window. First thing, the mesh will be in lightning symbol as well. So you have to click here with the CFD select here. And you select CFD and then you input element size to be 0.004, and then you also have edge sizing. Edge sizing, which is around the test section area here. I set it to 400 divisions with no bias. And now, since this is the unset student version, it has a limit of the number of nodes to be 43,000 nodes. So no, then the limit is 51,200 nodes. So I think after many try, I think 43,000 is like the maximum we can obtain here. And after we have done all the meshing, we end up with a name selection. The wall will be the order upper bound and the wedge. Symmetry will be on the lower bound. Inlet is on the left, outlet is on the right. And that's it for this meshing window. And then when you're done with mesh, you open the next box, which is fluent flow analysis. First thing when you're in here, you set up everything. Everything include your boundary conditions, the calculating model, everything. The first thing is the solver. We set it to pressure based. To this space will be planar because the MATLAB code has a limited, which can be applied to planar analysis only. The model will be inviscid flow. And the model is inviscid. And after that, we will set the boundary conditions. The inlet, as in the report, say that it will be 5 times the pressure ratio. So the inlet pressure will be 5 times how the pressure ratio would be. This one. And also the outlet pressure here. It's the outlet pressure. And then we set up the method for the density to be first order upwind. After that, and also the residue to have criteria of 1 e to the minus 6 in every residues. Continuity, accelerated velocity, ng. And then we initialize hybrid initialization, and then we run the calculation for 5,000 iterations. 5,000. After that, we've done, after it finished calculation, we will get the contour plot, which is what we need to see the result. And this is the contour plot. So the Mach number here, as you can see that the most reddish color shows us has a Mach of 2.5, which is right at the cone. This is what we need, and that's the maximum value. So the cone will reach Mach 2.5 per instruction. And also any other stuff as well. This is the static pressure. Static pressure like this. And also the total pressure and static temperature and total temperature as well. And that's all my part. So when I obtain all the contour plots that we needed already, and I will report the pressure value for my other teammates of mine to do the structure analysis on this same model, but it will be extruded into 3D stuff. Yeah, and that's all for my part. Thank you.